Hello, we are a team of bioengineering students that are researching and developing a transtibial prosthetic ankle which incorporates a muscle wire for use in developing agricultural countries.
So our global health challenge that is motivating us is of the 40 million amputees in developing countries, only 5 to 15% are able to receive a prosthetic. Many of the amputees rely on physical labor for survival. Therefore, it is imperative that they receive a durable and affordable prosthetic that can withstand cyclic use in uneven and rough terrain. The overall goal of any prosthetic is to allow amputees to return to daily activities and to do so pain-free. However, many low-cost prosthetics lack mobility, which can cause gait problems and lead to further injuries. The global health need for our technology addresses the need for the affordable and mobile prosthetics in many developing countries. As we said earlier, most of the prosthetics devices available today in developing countries are very expensive or not active, which can lead to difficulty walking and performing daily activities, as well as other indirect injuries. Our affordable, lightweight, and durable ankle prosthetic is semi-active and incorporates the natural shape and structure of a foot with the modern invention of muscle wire and implantation of pressure sensors to allow the ankle to move and respond to changes in terrain and achieve the flexation angles present in the normal gait cycle. This technology is to benefit amputees in low-income countries such as India, being current country of research and focus. The prosthetic is specifically designed for those in agricultural areas whose livelihood relies on their ability to perform physical labor.
We've designed an ankle prosthetic that relies on a muscle wire, which will simulate the natural mechanisms of the ankle. Our ankle prosthetic was designed and rendered in SolidWorks, and the kinematics of the foot were evaluated with Simulink. The muscle wire and pressure sensing components are integral to the dynamic function of the prosthetic, with materials carefully selected to enjoy heat, dirt, and humidity, all of which are encountered daily in agricultural settings. Muscle wire is a nitinol memory-shaped wire which contracts and extends when stimulated with electrical current. To understand the basic mechanical and material properties of the nitinol wire, stress-strain testing was conducted on it with and without electrical current subjected to it. The springs along the prosthetic's talocrural joint are responsible for absorbing shock in the coronal and sagittal plane, while the muscle wire is responsible for controlling dorsiflexion and plantar flexion movements. The low-cost pressure sensors attached to the sole indicate foot position. The position is then communicated to the prosthetic's Raspberry Pi, and a responding current is conducted through the muscle wire. This should enable the prosthetic to assist during the heel and toe off of the gait cycle. With these parameters engaged, the prosthetic offers stability, allowing the ankle to shift according to the terrain.
Our successes include the 3D design of the transtibial prosthetic that is capable of withstanding 9,000 newtons of force and can endure a lifetime of approximately 2 years, and stress strain testing of the muscle wire that has indicated promising use in the design to allow for ankle mobility. The next phase of the project is split between the muscle wire and sensor components. The properties of the muscle wire will continue to be evaluated to determine how to program the sensors to communicate with the muscle wire during the different phases of the walking cycle. Further steps would also include physical gait analysis studies, testing and implementation of the sensors into the prosthetic sole, and evaluating the optimal material to be used to create prosthetic.